So we'll, yeah, take off, have booster separation, go into parking orbits, do a translunar injection, fly around the moon, and then come back and land. The production design of BFR is different in some important ways from what I presented about a year ago. Overall, it is 118 meters long. BFR is designed to be able to take 100 tons all the way to the surface of Mars. You're able to get from Mars to the asteroid belt to the moons of Jupiter, and kind of like planet and moon hop all the way to the outer solar system. So BFR is really intended as an interplanetary transport system that's capable of getting from Earth to anywhere in the solar system as you establish propellant depots along the way. Yeah. The way that BFR flies is somewhat counterintuitive. If you apply your sort of normal intuition, it will not make sense. So there's the two forward actuated flaps, and then there are two rear actuated wings or fins or flaps, depending on what, they're not exactly comparable to anything else out there. So the way it operates is kind of more like a skydiver than an aircraft. Almost the entire time when it's re-entering, it is just trying to brake. It's just trying to stop. So it's doing everything it can to shed velocity while distributing that force over the most amount of surface area possible. So two of the three rear fins actuate. They're like giant wings. It actually requires an enormous amount of force to move those wings. It's sort of in the meganewton class of force. The third fin or wing-like structure is actually does not actuate, and it is not a vertical stabilizer as it may appear. It is actually just a leg. So this is a true physics simulation of BFR re-entering. So it is mostly just coming in like this. At a very high angle of attack. In fact, one of the things that, for the general public, is a tricky thing to understand is that orbit means you are zooming around the Earth at a very high speed. It's counterintuitive where people think perhaps once you get to a certain altitude, gravity turns off. This is not the case. In order to go up and stay up, you have to move around the Earth at approximately 25 times the speed of sound. So in fact, the space station is circling the Earth every 90 minutes. This is a very important concept to understand, that orbit is entirely about your speed horizontal to the ground or parallel to the ground. It is going up and staying up the only reason you need altitude at all is to get out of atmospheric drag. So if Earth didn't have an atmosphere, you could orbit 1 meter or like 3.28 feet above the ground, no problem. Well, a little dodgy, but it's technically possible. So yeah, if you looked at that simulation, it might be worth playing that again, actually. So you can see it's basically coming in, if this is the Earth, if this stage is the Earth, it's coming in like that. And it's just using its entire body to brake. And it sort of goes like that and slows down, and then it falls like a skydiver. And then it rights itself, fires the engine, and lands on the fins. I mean, this will look really epic in person. It looks like guaranteed to be exciting. And you can see it's sort of falling body first for quite a while. It's really quite gentle. You're just sort of falling at terminal velocity for quite a long time. Very gentle fall, just sort of like floating down. And then it rights itself at the end, fires the engines and lands. It's very counterintuitive. It's not like anything that people are familiar with. It's not like an airplane. Or, yeah. And then obviously, if you're landing on the moon, you don't need any aerodynamic surfaces at all because there's no air. You just need thrusters. So the next steps with BFR are we're going to build it, or we are building it. This is a picture of the main cylinder section of BFR. So BFR is 9 meters in diameter. It's really quite enormous. You can get a sense of scale. Like that's to scale. So that gives you a sense of the size of the vehicle. Quite enormous. But we're already building it. So we've built the first cylinder section. So that's the first actual cylinder section of the BFR prototype. And we'll be building the domes and the engine section soon. And then this is the Raptor engine. So this is the Raptor engine that will power BFR, both the ship and the booster. It's the same engine. And this is approximately a 200-ton thrust engine that's aiming for roughly a 300 bar or 300 atmosphere chamber pressure. And depending upon, if you have it at a high expansion ratio, has the potential to have a specific impulse above 380. But it's a stage combustion, full flow, gas. For those who are interested in technical details, I'm really excited about this engine design. I think the SpaceX propulsion team has done an amazing job on this engine design, and the SpaceX structures and aero. Like really, SpaceX team has done a phenomenal job in design of this. It's like super great. Like, well done, guys. I mean, like this is a stupidly hard problem, and SpaceX engineering has, I think, done a great job with this design. It's like I don't think most people, even in the aerospace industry, like know what question to ask. Like it took us a long time to even frame the question correctly. Like once we could frame the question correctly, the answer was, I wouldn't say easy, but the answer flowed once the question could be framed with precision. So we'll take off. Have booster separation, go into parking orbits, do a translunar injection, fly around the moon, and then come back and land. We'll do a bunch of test launches without any people on board before having people on board. To be clear, it's going to be very important to test this vehicle thoroughly before putting anyone on board. Yeah, but I can't wait. Like I'm super fired up about this. This is amazing.